We start a new chapter today, chapter 6, and today's topic will involve the graph of two different functions. We're going to be talking about exponential growth in the first half of the lesson, and then we'll talk about exponential decay. And we'll look at, in general, what these graphs look like. I'm going to give you a process on how to sketch those graphs. But before we get into the lesson, I want you to just take a look at this little video that is really a good illustration of how exponential growth works. This story, it's a legend that comes from the country of India, and just want you to take a look at it as we prepare to actually sketch the graph of these exponential growth functions.
This is an old story, but it reminds us of the surprises we can get when even a small number like 2 is multiplied by itself many times. King Shahram of India was so pleased when his Grand Vizier Sisabendar presented him with a game of chess that he asked Bendar to name his own reward. The request was so modest that the happy king immediately complied. What the Grand Vizier had asked was this: that 1 grain of wheat be placed on the first square of the chessboard, 2 grains on the second square, 4 on the third, 8 on the fourth, 16 on the fifth square, and so on, doubling the amount of wheat on each succeeding square until all 64 squares were accounted for. When the king's steward had gotten to the 17th square, the table was well filled. By the 26th square, the chamber held considerable wheat, and a nervous king ordered the steward to speed up the count. When 42 squares were accounted for, the palace itself was swamped. Now fit to be tied, King Shahram learns from the court mathematician that had the process continued, the wheat required would have covered all India to a depth of over 50 feet. Incidentally, laying this many grains of wheat end to end also does something rather spectacular. They would stretch from the Earth, beyond the Sun, past the orbits of the planets, far out across the galaxy to the star Alpha Centauri, 4 light years away. They would then stretch back to Earth, back to Alpha Centauri, and back to the Earth again.
So the exponential function that was illustrated in that little video was y equals 2 to the x power. So each square, like the first square would be 2 to the first, and then the second square was 2 to the second, that's 4, 2 to the third, it's 8. And then by the time you got to, there's 64 squares on a chessboard, 2 to the 64th power is over 18 quintillion. So I just thought that's a good representation of how exponential growth works. So let me give you some practical steps in what you're going to be doing on your homework. So we'll start with this basic exponential growth function that you saw in the video. So here's what I want you to do when you do your graphs. You're going to give me a table, and just to keep this standard, I'm going to ask you to use the same 5 inputs every time. Okay, and I understand that you could use any input you want. Technically, this is the independent variable. This is the dependent, but just to make it easy for sketching and comparing grading purposes, we're going to do these inputs. So 0, positive and negative 1, and positive and negative 2. All right, so those are going to be your standard 5 inputs. And now let's take a look at what we get as outputs. So if we raise 2 to the 0 power, remember, if we take a base and raise it to the 0, that's going to equal 1. If I raise 2 to the first power, I've let x be 1, 2 to the first is 2. If I let 2 go here for x, that's 2 to the second power, which is 4. If I let the exponent be negative 1 and 2 to the negative 1, remember we've had this discussion quite a bit about negative exponents, and that forces me to flip the base over, so the reciprocal of 2 is 1/2. So it makes it 1/2 to the first power. And when I let x be -2, I get 2 to the -2, which is 1/2 squared, which is 1/4. So you see how the negative exponent really just produced the inverses of their positive exponent counterparts. All right, so let's sketch this and get a general idea of what exponential growth looks like. So it's typical that we're going to have a y-intercept of 1. All right, there's 0, 1. And I'm going to plot the point 1, 2, and then 2, 4. Okay, and so you can kind of get an idea as you flow from left to right, as our values for x get bigger, this is really taking off pretty quickly. I mean, just imagine if we did 2 to the 5th power, where here's input 5, we would have 32. Okay, 2 to the 5th is 32. 2 to the 6th would be on a higher than that, double that, that would be 64. So you don't have to go any further, but I just want you to show that the graph is still going to continue in that direction. And now let's plot our negative numbers and see what happens as we approach negative infinity with our inputs. So for input -1, we get output positive 1/2. Input 2, we get output 1/4. So just the opposite is happening as I choose numbers going to the left. I'm getting closer and closer to the x-axis. As I move to the right with my inputs, I'm getting further away. So here's the general look. This is specifically y equals 2 to the x, but this is what exponential growth always looks like. We say that this graph is increasing. So for graphs that are increasing, we're always talking about from left to right. They are approaching positive infinity as x approaches positive infinity. All right, so this graph is increasing. There's something else that's interesting, and I'm going to put a term here for you that I want you to put in your notes. Do you notice that as we go to the left, as x approaches negative infinity, we are getting closer and closer and closer to the x-axis, but we're never actually going to get there. If you think about it, getting to the x-axis would mean that there's a number I could put in for x that would make y equal 0. Well, there is no number that I could put in for x to turn this y into 0. It's not possible. So I will get very close. If I let x be -1 million, I'm going to be really, really close, but 2 to the -1 million isn't 0, so I'm not actually going to be on the x-axis. So this brings up a term that's going to come up again in future lessons. Whenever we have a graph that continually approaches a line but never actually gets there, we call that line that we are approaching, here's your term, it's an asymptote. All right, and so for this particular graph, the x-axis is called a horizontal asymptote for this particular graph, this exponential growth graph. All right, and now we state the domain and range. Well, the domain, as you can probably see, is going to be all real numbers. We're going to be forever going left on the x-axis, and that's also going to be true as we move to the right and up. So it's going to be always true. It's going to be all real numbers. And for now, you can just state it like this. But the range is starting at 0, but 0 is not included. We've already discussed how we'll never be able to input a number to make this become 0. So our range is going to be the y's such that y is greater than 0, but it's not going to be greater than or equal to, just greater than. All right, and so there's your answer for that first example. And now let's talk about some transformations, just like we've done in the past. Okay, so I've taken this same exponential growth function, y equals 2 to the x, and notice what we've done. This indicates a shift of 3 to the left, and this indicates a shift of 5 down. So those same transformation principles that we've talked about with other parent functions are still being used. All right, so here's what I want you to do on transformations. I want you to graph showing me a progression through tables. So once again, you would show me the parent table, y equals 2 to the x. We just did that. 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4. And then you can just do this in one table. Show me how moving left 3 and down 5 impacts this, and then you will graph that table as your answer. So I'm going to call this left 3 and down 5. Well, using a table progression, left 3 would mean that I would subtract 3 from each of the x's. Okay, I'm just going to do that now. 0 minus 3, 1 minus 3, 2 minus 3, negative 1 minus 3, and negative 2 minus 3. Okay, so that accomplishes the left 3, and now I'll just use the same table and you can do down 5. So once again, that's going to be subtraction. 1 minus 5, 2 minus 5, 4 minus 5, 1/2 minus 5, that's negative 4.5, and 1/4 minus 5, that's negative 4 3/4. And obviously, if you need to use your calculator for those, that's no problem. But this is the table that I'm actually going to plot as my answer. I'm okay too. If you want to just plot like we've done in the past, you could plot these. And let me just show you what I mean. Just like we did on the previous slide, you can plot these parent points and then literally move them left 3, down 5, and then plot your answer. You don't have to connect the parent, but if you want to use these as reference points, but I do want you to show me your table. Okay, make sure that for every one of your final graphs, you have a table that matches what you've sketched. All right, so let's take a look at what this looks like. Negative 3, negative 4, right there. Negative 2, negative 3, negative 1, negative 1, negative 4, negative 4.5, and then negative 5 is going to be a little bit lower than that. All right, so do you notice how the parent had a horizontal asymptote of the x-axis, but according to this, we shifted down 5, so that meant our horizontal asymptote now is this line. You don't have to draw this line. I think it's a good idea if you do, but if you don't, you just have to be aware that you should not go below this line. Okay, just like you didn't go below the x-axis, well, now you're not going to go below y equals negative 5. All right, so it's going to be something like this. Okay, and that is your answer for example number 2. And now let's do same thing. We're going to put a number here. The only difference is in our previous example, I didn't have a number here in this A spot. It was just assumed to be 1. Well, let's see what this does. Okay, just like we dealt with this with square root when we had a number in front of the square root. We did the shift. So same type of deal. Okay, we're still, just like we did with the square root and the cube root, we're still multiplying this number times just the y coordinate of our parent table. All right, so first, let's get a table for the parent. So the parent is just the base of 6 being raised to the x. All right, and so here we go. Use those same 5 inputs. I'll make it easy on you. You should never have to question, what do I input into the parent? It's those numbers every time. 6 to the 0 is 1. 6 to the first is 6. 6 to the second is 36. 6 to the negative 1 is 1/6. 6 to the negative 2 is 1/36. Okay, now my next table, as I work my way through this progression and I do the transformation rules, is I do times negative 2. And again, just like we've talked about in previous lessons with other parent functions, this is just the y. just the y times -2. All right, so in this table, I don't do anything to the x's yet. If I just want to show, this is called vertical stretch, and we also have a reflection. So I'm just going to multiply each of these y coordinates by -2. So 1 times -2, 6 times -2, 36 times -2. When I multiply 1/6 times -2, that's -2/6, which is -1/3. And this would be -2 over 130, or -2 over 36, which is -1/18. Okay, and now I'm going to do the shift, and notice that there is no h number, so there was no horizontal shift. So when I do this final table, there is no left-right movement. There's only a down movement. I'm going down 3. Okay, so my final table, just do it in red. My final table, I'm just rewriting these x coordinates. Nothing changed. I didn't move horizontally. But to accomplish down 3, I'm going to take each of the y coordinates and I'm going to subtract 3. So -2 minus 3, -12 minus 3, -72 minus 3, -1/3 minus 3, -3 1/3. And -1/18 minus 3, -3 1/18. All right, so this is my table that I'm actually going to plot and graph. And I noticed that, wow, these are pretty big numbers. So here's a case where you might want to consider at least, you don't have to change the x-axis, but you definitely would like to change the y. So since I'm dealing, looks like in 5s here for the most part, I'm just going to make my y-axis in 5s to make this fit better. All right, and we'll just leave the x-axis alone. So 0, -5 then would be right here. 1, -15 would be here. 2, -75, that would be 15 units. 15 times 5 is 75, so 2 and if I can go to 15 or not, I'm just going to put it down here. We'll call that 15 units or -75. And then -1, -3 1/3. So just approximate, since that's 5, it should be a little bit beyond halfway. -2, and that should be a little bit higher for -3 and 1/18. Okay, so my graph, remember we had a horizontal asymptote of y equals 0 for the parent. Well, now you can always look at your vertical shift and it'll tell you what your new horizontal asymptote should be. So in this case, it should be y equals -3. Now it looks kind of weird because remember these are in 5s, but I'm just going to estimate, I'm going to do a little line here. And this is just a rough sketch, but I'm going to say this is y equals -3, and we should not go above that line when we sketch our graph. I hit that bottom point. So this is actually called negative growth. Negative growth, very common everyday application of negative growth would be our national debt. It's growing exponentially, but unfortunately it's growing in the wrong direction, in a negative direction. So that would be an example of a transformation where we have a number here. So every time you've got a number in this A spot, you just multiply that number times the y coordinate of your parent table, and you should be good to go. So let's do domain and range. Domain is still going to be all reals. And for the range, we are going to be less than -3. okay, all the y's, such that y is less than. Now it's not going to be or equal to, so we're never going to get to -3. It's just going to be all the y's that are less than -3. Okay, so there's some exponential growth. Well, the good news is when we get to exponential decay, it's really the same thing. It's just the thing that causes you to recognize that this is decay and not growth. It's this number here under the exponent. Okay, so for growth, this number, this base, will always be greater than 1. All right, so let's just go back and look. See how I've got a base here of 6, greater than 1, I got growth. I've got a base of 2, greater than 1, I got growth. Okay, so that's the thing that distinguishes in function form growth from decay. It's this base number. So you'll know you're dealing with decay if this number that we call the base directly underneath the exponent x, if it's between 0 and 1. All right, so we'll just say it like this, and then using inequalities, we could say it like that. Okay, could be 0, it'll be bigger than 1, okay, for growth, and less than 1 for decay. All right, so let's just take a look at this decay graph. Very similar. We're going to use those same inputs. So 1/3 to the 0 power is 1, 1/3 to the first is 1/3, 1/3 to the second is 1/9. When you raise 1/3 to the -1, that makes 3. To the -2, it makes 9. All right, so once again, we have the same y-intercept that we had for growth, but notice a big difference in the way the graph looks. When I go to the right now, my inputs get bigger as x approaches positive infinity. Now my outputs are getting closer to the x-axis in this direction. So I'll call that 1/3, 1/9. And that's just going to keep on happening. I'm going to be approaching the x-axis this time on this side of the y-axis toward positive infinity on the x. And then as the numbers get smaller for x, like -1, output 3, -2, I think that's up here at the top, output 9. So you see decay is going to take on this shape. All right, so if I can hit my dots. Still have a horizontal asymptote for the parent. It's going to be the x-axis. We're just approaching it from the opposite direction. Okay, domain and range are the same. Domain's still going to be all reals. Range still going to be y's that are greater than 0. It's just the way the graph looks. So growth will take on this shape. Decay, just the opposite. But I'm hoping my video is getting a little bit long here. I'm hoping that you can do the graph of decay because the processes are the same. Okay, let me just kind of get you started, and you won't have to watch the rest of this. So when you're graphing decay, you start off with a table for the parent. Okay, so just like you did for growth, 0, 1, 2, -1, -2, and come up with the what we would call the parent points. So 1, 1/4, 1/16, 4/16. Okay, now vertical stretch. And if you're really good at this, if you want to do ×2, left 2, down 3, all in one table, and you feel comfortable with that, then by all means, if you feel like you can do it and get it right, then that's fine. I'm going to break them up into 2. So remember, just the y times 2. All right, I have vertical stretch, so that doesn't affect the x's. So 1 times 2, 1/4 times 2, 1/16 times 2, 4 times 2, 16 times 2. And then my final table, the one that I'm going to graph, is going to show left 2, down 3. All right, so for left 2, I subtract 2 from the x's. 0 minus 2, 1 minus 2, 2 minus 2, negative 1 minus 2, negative 2 minus 2. And I subtract 3 from the y's to do down 3. 2 minus 3, negative 1. 1 half minus 3, negative 2 and a half. 1/8 minus 3, negative 2 and 7/8. Let's do that in fraction form. All right, 8 minus 3 is 5, and 32 minus 3, 29. So this ends up being the table that you plot, and it should take on that basic shape, although remember it's been shifted down 3, so you have a new horizontal asymptote. So you're going to be approaching this line, y equals negative 3, as your graph comes down and approaches as x approaches positive infinity. All right, so I think I've done enough to help you. There is one more. I think you can skip that one and let you go ahead and get started with the assignment. And if you do have any questions about this, you're welcome to email me or come see me tomorrow morning during academic support.